time domain, and you can transform one-dimensional spatial domain. So you can see there is time signal, the component, and cosine 40 plus some phase shift, sine 80, and 4x, and 1 is omega. Omega equal to 2 pi f. So if you together, and repeat the signal, and when you get the signal, you can see different components. A1 times 90, A2 times A3 times. So actually, the component in briefly domain. So into we get at the first second 40 the original here. And so you can want to look at your signal in briefing domain. So here is some MATLAB function. You can go home and try it and add some different frequency component at different coefficient. The coefficient here means it's amplitude. Okay, different amplitude. So it will dominate your signal if it is a larger amplitude. Okay, you can try this one at home. So here's just give you some idea. If I have different different component, actually they have the same frequency component, but with different amplitude, and you can see like this one. Equivalently, for different component is a shape like this one. Okay, like this signal. And if you have a larger low frequency component, this will look like this one. If you have a larger higher frequency component, this will look like this one. So from different signal, actually you can expect what kind of component, what's the partition of the component occupied in this frequency. All these four signal, they have only three frequency components. Okay, and this signal is reflective. It's a periodic signal, composed like this one. Okay, you can play around if you use MATLAB to do it, and you can look at it. So we just made for the T, and you can see if we give the full condition. Fundamental frequency times omega 0, 3 times, 4 times, blah, 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 to infinity. So you can use your signal can be like this formula. So every periodic signal can be written down like this one. So it's including all different coefficients, all the different harmonic waves there, right? So every periodic signal, if we write this one, xt equal to xt plus capital T is your fundamental period, okay? So you can write down your signal like this one. So you can assume your signal, periodic signal, contains all the different amplitude, all the different harmonic waves there. Okay, so in that sense, we have to know what's the coefficient of An, what's the coefficient of Bn at n times harmonic wave. So you have to calculate. So in this this is just a mathematical to see. So we call it a trigonometric. In Chinese is 三角傅立叶转换三角傅立叶级数. Okay, so it's a trigonometric formula to try to look at the periodic signal can be decomposed. If this is periodic, can be composed all the different coefficients combined with different frequency component. Okay, and so how you calculate? This is the formula. Okay, so I can find out the C0. Actually, this is a DC component. So your signal, if this is not average 0, this must be some value of C0. If your signal average is 0, the C0, there is no DC value here, so it's become 0 here. And An for cosine for component like this one, Bn like this one. So you can do this calculation to find out every component, the size of every component. Okay, so this is we call it this is trigonometric Fourier representation, but we can use another format, mathematical format. We call it complex form. Not use trigonometry, not use cosine, sine. We use what? We use exponential Zn omega 0 t. Actually, it's also a component omega 0 as a fundamental frequency. And the n is the harmonic wave, how many times of your fundamental frequency. So you can see from cosine an cosine n omega 0t plus bn sine n omega 0t, you can combine, change it to as a complex form. Let's see, this is Euler. We say it is Euler. Cosine. So it's an Euler. Euler form. Signal, you can use this kind of formula to represent it, similar to our trigonometry, but it's in exponential form. So it's the relationship like this one. So from here you can change to this one. Cosine equal to this one plus this one divided by 2, and this is minus difference divided by 2j. So it's become complex form. Okay, so the relationship like this one. So here is the Cn. How you calculate this one? So Cn is become the amplitude of h1 omega 0 and omega 0. What's the harmonic wave amplitude? Becomes Cn. It's not an An and Bn anymore. It becomes Cn. But Cn, the relationship between Cn component amplitude and An is like this. Cn is like this one, and An is like this one. Bn is like this one. So they can change. So if you have your periodic signal in trigonometric Fourier series representation, you can change to complex form. If you in complex form, you can change to trigonometric form as well. So they can change to each other through this relationship calculation. Okay. So depend on what kind of representation you would like, complex form or trigonometric form. Okay, so here's an example, because we are looking at this many times, okay, even in the image, okay. So you can see it's a periodic signal, right? You can see this rectangle post, and then it happened at a t, happened at 2t, there's another one, happened at 3t, another one. Okay, so it's continue occur, this kind of rectangular way. Okay, so in one dimensional, but in two dimensional is like a cubic, like a tofu. Okay, in two dimensional. Okay, so in one dimensional you can see it's right on xt equal to a, the amplitude a, and then between t divided by 2 minus t divided by 2 plus t divided by 2, and the peak is a capital T. So it's the range should be like here, right? So in the whole period, the next period is happened to 2t. So also it's tell you there's a signal. The width of the signal, the temporal pulse is t seconds, within capital T seconds. So there are two parameters you have to know. First is capital T. The second is small t. But I'm telling you, there is a repetitive signal in capital T second, and the width, the pulse, is t second. So there are two parameters for this repetitive signal, right? And so let's try to use this complex form to represent this signal, because we know xt plus t plus capital T is the same. It's a repeat signal there. So I can change it from time signal into complex form Fourier series, right? So as long as I can calculate the Cn, I know what's the amplitude in frequency domain. So the Cn here, the amplitude is exactly the size, the amplitude in that specific frequency component. N0 is the DC value. N1 is the fundamental frequency. N2 is the second time of your fundamental frequency amplitude. So you have to calculate C0, C1, C2, C3, and see how your periodic signal arrange, occur, distributed in your frequency domain. That's the energy. Yeah. If you take the square of this coefficient, it becomes the power of your signal. So you are going to decompose your signal and into frequency domain and look at the energy of your component, different components in frequency domain. Okay, so if you look at your original time signal, you can see nothing there. But if I can decompose into frequency domain, and I know the amplitude, I know the amplitude, I know the amplitude, and I can know what's the energy in different components. So I can remove the high component, I can remove the low component. It's become of the low pass filter, high pass filter, depending on your design. So what you have to know, what's the Cn here? Cn is the amplitude of your frequency component, amplitude, okay? And the square is the power. We call it power of the spectrum. Okay, yeah, so it's easy, calculate that this way. So as long as you know it's a repetitive signal, periodic signal, I can calculate every component in the frequency domain, the amplitude goes through this transformation. Yeah, so it's an idea, right? So as long as you know your signal is repetitive, and I know every different harmonic wave, amplitude of harmonic wave, and I know the energy distribution. So if you have this square the range is minus t divided by 2, positive t divided by 2, but only from t to divided by minus 2 and the t divided by 2 have the signal. So in this calculus, I'm not going to do that. You do by yourself. So Cn equal to what? Actually, only occur in this range. Only occur in this range. Non-zero, right? And the amplitude of this one constant A, because all the signal is a constant. It's a the rectangular pulse, and then times what? So you have to calculate this one. Do some calculus integration to solve this one. If you don't know how to do that, come to me, okay? During the office hour, I can teach you step by step. But I'm not going to do here now. And the result like this one. Go to here, okay? Exactly the result is the sine of some component here. You can say sine of x divided by x. So that's what we mentioned in next class. It's a sine x divided by x. We define it as a sinc function. So the sinc function of maybe we say sinc function of x equal to what? Sine x divided by x. Okay, so it's a x component here, sine x divided by x. So sine is between 1 and positive 1 and minus 1. But x increases. Even x increases, sine also constrained within the positive 1, negative 1. However, the denominator x go to infinity. This one becomes very small, small and small, come to 0. So the result of this one is like this one. So it's like a sinusoid, but when t is when this is higher in frequency domain higher, but the amplitude becomes smaller until to 0. So the sinc function in frequency domain omega is just like this shape. Okay, sinc function. So I want to let you know your transformation from this one continue is only spectrum. Sorry, they only have an amplitude. So if you see amplitude, there's no this continuous wave there. So it should be look like this one. There's only spectrum here in different multiple harmonic wave components. There's an amplitude in N1, N2, N3, N4, N5, N6. So it's a nice spectrum. So if you have a repeated signal, periodic signal, in frequency domain, only the specific fundamental frequency, and then multiple harmonic wave have the energy. So it's a nice spectrum like. It's a 9 by 9. Okay, nice spectrum. Okay, so that's just like this one. Okay, if we have this D is 1 divided by 20, so it's 1 divided by 40 minus 1 divided by 40, so it's the d equal to 1 divided by 20. And the next occur is t equal to this example 1/4. So happen to here again here happen to here minus 1. Okay, go to infinity. So if you have a periodic signal, rectangular pulse with a t like this and a t like this. Okay, now we are going to change what? Change the capital T. What's your duration? Your periodic signal happen in the next repeated signal there. So become larger and larger, become far and farther. So what's the result? The second one will be happen like this one. The first here, the second one will be here. Okay, double. The second one will be here. And the third one, this one, will be even farther. So the second repeat is far away. So that's the example we'll try to tell you what the result will be. So that's the first one. Capital T here. This is the capital T equal to 1/10. This is capital T equal to 1 second. So why? So you have to think about it one. My D is the rectangular force exactly the same width. Okay. But my repeat signal, the time is different. The first one is shorter, the second one in the medium, the third one is the largest one. And the result like this one. Why? Remember what's the omega n omega 0 here? What's the fundamental frequency? Omega t equal to pi, right? So omega 0 equal to 2 pi divided by capital T. So omega 0 is your fundamental frequency. In Chinese, 基本频率. And the next one will happen in 2 omega 0. And the next one will appear 3 omega 0, 4 omega 0, 4 omega. So it depends on the fundamental frequency. It's a 2 pi divided by T. So T is in denominator. If your T is smaller and the receive in the denominator, it becomes larger. So we have 3 different capital T, right? We have a 1/2, 1/4, and half, 0.5 second, and 1 second. So what's the result? So if you divide a smaller capital T, the result will be larger. So which means this is the first one, this is 0, okay, 0. The next one is the omega 0 here. Omega 0, 2 omega 0, 3 omega 0, 4 omega 0. Now we have different T. This is larger T. So when your denominator is larger, your omega 0 becomes smaller, right? So what does that mean, smaller? Smaller becomes higher dense together, become higher density. And for the third one, the largest T become very, very, very dense compared to other two frequency domain. But they happen to the same. Sorry. Can I control it? Okay. The same close layer. But with different density. T is larger, becomes denser. T is smaller, becomes sparse. Okay, becomes sparse. So it depends on your repeat signal when it happens. Okay, so now let's change to here. We have the same T, but different rectangular pulse. The T is different. So what's the result? Can you expect? We have 2 different parameters, and we fix one parameter, change the other one in 3 different cases. The second point we have the same periodic frequency in time domain. The wave the same, but with different rectangular poles. So what does that mean? We have three signals in time domain. It's like this one. The second one is happening here, and the second one is the D is larger or smaller, but happen at the same time. And third one is even smaller in half width, right? This example. The T fundamental frequency happens the same. T the same happens here. The second pulse, but width is from largest medium to smallest size. So what will happen in your breathing domain? What's the difference? So remember, the omega 0 depends on capital T. So it's 2 pi divided by 2 at T. And T is the same. So which means your line spectrum distance is exactly the same because omega 0 is the same. So every distance between these three signals, they have the same width. But when this is smaller, D, we should say small d, and its n will become larger. It happens in different locations. So this is just as you know, if you have a thinner width, and in breathing domain, you will have a wider spectrum. For this example, so if you have a wider rectangle pole compared to the other two, but this is just inverse, different relation. Okay, this one is the largest rectangle pole. This is medium. This is the smaller. So, in different aspects, time domain, frequency domain, exactly reverse condition. Okay, so you have to go back to look at this one. You can calculate, do this one together, because when it happens to 0, depend on the n. So we can see the n here for a wider width, wider rectangle pulse. In here happen earlier to 0, and you have a narrower rectangle pulse. The first 0 point will happen far. So, but they have the same line spectrum distance. Then density. Okay. So, this is the idea. Tell you if you have this very easy repeated signal like the rectangle pulse and their condition, you have to know what's the key feature. We have to look at it because we are going to design our filter. We have to know this one. What they happen. Okay. So here is the same function. Give you some method, you can try to do it. Okay, it's a sine pi x divided by pi x, right? Remember, it's dot operation. The vector have to use dot operation, so don't miss this one. Okay, when you type, don't miss this one. They were corresponding pixels divided by each other. Okay, it's not a traditional vector vector multiplication, vector division. No, it's corresponding pixel division, corresponding pixel multiplication. Okay, so the vector operation in MATLAB is different. Okay, so you can type this one and play around. Okay, how can I find the usage, the same function here? Okay, so you can see what's the same function in different condition. Okay, just give you some. But remember, your wider signal in time domain and become narrower. If your narrow width narrower, okay, in time domain, in frequency domain become wider, the image will see that later. Okay. What I want to say is this one. I give you the example of this function. We call it comb function. Okay, comb. Just like you comb your hair, right? 梳子函数 comb your hair. Okay, like a comb, right? Actually, it's delta t minus delta t, and this is the second impulse delta t minus 2t. This is the minus t, so it's a delta t plus t. Delta t plus 2t. So you can see it's go to infinity because it's a Hom function. What's this function for? If you are going to do some digital signal processing, digital image processing, digital speech processing, you have to know this signal very well. Why? Because you are going to sample your signal. Sample, okay? You are going to do in your computer. You have to do sampling first. Because all the voice we're talking about is a continuous signal. All your image you look at is a continuous signal. You can't do it in computer. So you have to teach your signal first. How you teach that? You have to sample. So how to sample? As long as your signal multiplies with this signal, you are doing sampling process. Multiply, right? So if I have a signal, voice signal like this one, times this Hom function, which means you are going to take the point of here. You are sampling. Sampling function. So we call it sampling function. Because it is a Hom function times your continuous signal. You can get this one, get this one, get this one, get this one at a location, specific location. So the key issue of the Hom function is the T, capital T, when it happens. When is the delta function located at? So T larger, which means your sampling very slow when capital T is large. When T is very small, which means your sampling time is very short, you will get a higher resolution. Okay? Is that right? If your capital T is large, because you second this time and next time it will be longer time. If you have very short T with a high resolution, immediately you will sample the second point. So it depends on the density of this function for the sampling time. So what's the Fourier transform in frequency domain? Can you expect this function is very specific? Okay, delta function. Delta function is defined like this one. The delta function is it's like this one. Okay, it's only occur at 0 point at time 0 there. There's an impulse, and it's area equal to y. How do you get this one? Actually, it's also from rectangular force. When you squeeze down the rectangular force, and the rectangular is an area with area 1, and you squeeze down the width, the height will double. And you limit the width into very, very small, the height goes to infinity. So there's an infinity height when you limit at a 0 point. So it's like an impulse there. And the area also maintained as 1, area 1. So integration will be 1. So there's a definition of the delta function there. In digital, we only tell you this is 1. The area already 1 there. This is the frequency function of the Hom function in time domain. It's also a periodic signal, right? So please do that one. We tell you it's capital T repeated with capital T, and I can represent as a Fourier transform, Fourier series, right? In complex form. Here times e to the n omega 0 t. So it's a previously slightly defined. As long as your signal is a periodic signal, I can represent it like this one. But I have to tell you what is here there. What's happen? The n omega 0. So what's Cn? So by the definition, Cn, the coefficient is take this repeat signal, and then times Ej minus n omega 0 t. Please do the integration. And here's the process. Tell you how to do that one. And I tell you it's only happen if you upper limit, lower limit cover this delta function. Their area will become 1. And there's mathematics should be okay. This is a basic minus a times f of t, t. Okay. What's the result? What's the result? The data may occur in different locations. The result, if this function times some function there, the result will be repeat this one, and t will be replaced by the location of the data, because the area is 1. So that's exactly integration result. So mathematically, it's a formula. Any function times this one, and integration, the result will be this function itself replaced by the parameter, replaced by the location of this data. So it happens at the A point, time equal to A. So just replace that. So by definition here, here's a function, f of t, right? And the result will be this one, and then replace the t by 0. Okay. E omega t, t equals 0, e minus n omega 0, t equal to 0. So times 0 there. So can you tell me any function, the power of 0 equal to what? Any function, yeah, 1 equal to 1. So exactly is equal to 1. This one exactly equal to 1. So the result will be 1 divided by t. So what's the result mean? For different harmonic wave location, their type, amplitude, always equal to 1 divided by t. Always. So that's the result. The result of the integration change into Freedom domain. It's still a Cohn function. So in time domain, there's a Cohn function. Here transform, look at Freedom domain, also a Cohn function. But the width is different. The width is omega 0 is 2 pi divided by t. So depending on your repeat signal, when it happens, the capital T, if the t is larger, the t in the denominator will become smaller, become denser. If t is small, the next sampling time is small. But t is small in denominator, so the next Tn will be far, right? Become denser, sparse, become sparse. Sorry, or become sparse, become far away, become very sparse. So now you understand. When I'm sampling your signal, the Cohn function will occur in different ways, and the amplitude is always 1 divided by t. So later on we will see. You are going to sample. You are going to use high resolution to sample your function, your image, or low repeat signal to sample your image will have different results. Okay. Okay. So let's keep this in your mind. The Cohn function, sampling function. You have a dense Cohn, you become sparse Cohn in frequency domain. If you have a sparse sampling function, you become a very dense Cohn function in frequency domain in different aspects. Okay, so I'm going to jump this one as well because it's already do that one. It's a sinc function, so you can just try to follow this one to draw the sinc function. Yeah, this is for the non-repeated, non-periodic signal. Okay, originally we have this periodic signal, right? And we are going to increase your next signal far and far in time domain. So it can be done t go to infinity, and it becomes non-periodic signal. So what happened in Fourier domain? What happened in Fourier domain? As you know, we have a periodic signal, and in Fourier domain we have a spectrum. And I just tell you, when your t is larger in time domain, in Fourier domain it becomes denser, right? Become very dense, very high density. And when your t goes to infinity, so what happens? You are connected together in your Fourier domain. So your Fourier component will become continuous spectrum. Original periodic signal Fourier domain will be 9 spectrum. You can see a lot of 9 in Fourier domain. But when your signal becomes non-periodic, all the nice spectrum close together, some continuous spectrum. Okay, that's just idea here. Okay, so we will see it's become Fourier transform. Okay, it's not Fourier series anymore. It's become Fourier transform and the inverse Fourier transform. So that's the terminology you have to know. Okay, Fourier transform is for signal is non-periodic. If your signal is periodic, you will have a Fourier series. You have nice spectrum. But your capital T, repeat T second, go to infinity, which means it's never periodic anymore. And in frequency domain, become continuous spectrum. Okay. This example. So previous we have a rectangular repeat signal. Now we don't have periodic signal anymore. I cannot find the second rectangle pulse because the capital T goes to infinity. So the result will go to like this one. And also you can draw this picture. It's become like this. Okay, the amplitude like this. Because I take the absolute value. So the next sign goes to positive. Like an amplitude spectrum. So it's the same function. Okay, but continuous. It's not nice spectrum. Okay, so non-periodic signal in frequency domain, continuous signal there. So it's the way you look at the Fourier transform. We have a time continuous, frequency discrete. We have a time continuous, frequency continuous is a Fourier transform. We have a discrete, so we can sampling your signal in time domain. So your time becomes discrete and frequency become continuous. So we have a following the discrete Fourier transform. So it's go like this way. Go like this way. So if you want to learn the digital signal processing step by step, okay, find out it. But we are not going to do it now. Just give you know there are some property of the Fourier transform. You come back to check it. Okay. If you want to find out the property of the Fourier transform in time domain, free domain, check out this table. Okay. So it's a linear relationship. Okay. See, xt Fourier transform x omega, y Fourier transform y omega. So in time domain, if your signal, your image multiply some constant, and add to the other image multiplied by some constant, in their Fourier transform, in Fourier domain, exactly the same because there's a linearity of Fourier transform. And they also have the time shifting. In time domain, you shift in some second or some location. In frequency domain, you are going to time some this exponential component. Okay, depending on how many seconds you shift. So they'll do some complex number there, like a scalar. And frequency shift. So if you frequency shift your image in your frequency domain, your energy domain, frequency spectrum, and in time domain, you are going to multiply this one. Very complicated relationship. And I think the most important is the convolution. I will just mention convolution. If you convolve your two signals in frequency domain, it becomes multiplication. Okay. If you do multiplication in time domain, it becomes convolution in frequency domain. So this conjugate relationship is very important. Why? Think about that one. If I multiply the home function here, that's my image. I'm going to sample. Okay, I'm going to sample your signal. What do? You multiply the sampling function. You multiply the home function times together, right? So which means what happens in frequency domain? It becomes your x omega convolution with the home function. Because the chapter 4 at the beginning they just show you this example, but I will explain why. Because they multiply the home function. They are sampling your image. And what happens in frequency domain is your image spectrum convolved with this sampling function, y omega there. If y is the home function, also you have to know how you sample it. And it depends on your sampling time, sampling spatial resolution. Okay, if you have very dense, very quick, very shortest time of sampling, in frequency domain, you become wider, become sparse. So they will not overlap. The convolution will be fine. But if your sampling time is too large, resolution is too high, you have trouble in Boolean domain, and the result will become some problem will happen. We will see immediately. Possible theory is just the energy distribution. You can calculate in time domain, spatial domain, and also the same, your frequency spectrum, take the square, take the integration, also take the same energy analytics. So that's the property of Fourier transform. Actually, you will just use this relationship. So most important here, because we are going to do some filter design, we are going to do some sampling process. So we have to know what's the result between these two. Okay. Please remember the relationship. Okay. And here give you some basic transform pair. Okay. For example, like we demonstrate like a rectangle function, the Fourier transform will become sinc function. How about others? Like a unit step function, like a delta transform is become constant. And if you find some exponential signal in your time domain, you'll become like this one. Okay. And like whatever, p tau t. This is the time domain with tau second. Okay. This is p tau t in time domain, the rectangular pose. So what's the result? The p tau t we just demonstrate is a sinc function, like a sinc function. Right? Okay, so give you some idea, transformation pair. Okay, and the sine, cosine. Actually, for the sine function, the sine become a two impulse happen at the omega 0 and the minus omega 0. Cosine also, there are two delta. So for the one sinusoid signal in time domain, in spatial domain, in Fourier domain, they only have a spike, two spikes. Okay, in the corresponding location. So we mentioned we found Fourier series to Fourier transform, and then we are going to sample our signal to digital signal, Cohn function, and it's become digital. So actually, this one can be changed to like this one. So we call it a discrete time Fourier transform. Why discrete time? Discrete time is you sample Fourier transform. Okay, DTFT. So that's the standard process you have to know. Fourier series, Fourier transform, discrete time Fourier transform, digital Fourier transform, phase Fourier transform. So all the process go like it one by one step, but don't worry. We will see that result. So this is the you can see repeated signal like this one, and actually like this one you'll get this result as well. Okay, so it's just a conjugate discrete time Fourier transform result here. So I think here just give you some idea of the Fourier transform because we are going to explain our this is chapter 4 here, right? Chapter 4 here. Okay. Chapter 4. Okay, thank you. So now it's easy for me to go back to look at this signal, very easy, right? The rectangular is a sinc function in a Fourier domain. And now we are going to sample our signal here. See, Cohn function. Now you know it's time domain. We are going to sample your signal there, right? What do? You multiply these two together. So become this result. So we are going to sample this function and become this one. Only specific time point, you are going to get it. Okay, discrete time signal there. And actually for the digital, how do you change it to digital? This one may be some continuous real number, but your computer you cannot solve it. So you have to decide how many bits are going to represent one signal. If you have an 8 bit, so you can change it to 0 to 255, and then some integer, and then do some process there. Okay. So now the problem is here. Illustrate the sketch of Fourier transform of band limit function. Remember, it's a FU. Okay, so here if you read your textbook, remember they changed T to U. I think they use this one. The parameter. Some of them use omega. Okay, T to omega, Fourier transform, the parameter. And some of them to change to UV, X to U, if you two-dimension, Y to V. Okay, so we have like a two-dimension f of x, y, e minus j omega u, omega v, dy is become f of u v. Okay, so when you look at the parameter, don't be visual domain or Boolean domain, depending on how you define your parameter here. So sometimes, most of the time, you have T to omega, okay, or T to x. It's a time domain to Boolean domain. Omega equals to 2 pi x, okay, 2 pi times x. And the u is location, so x may be to u, y to v. So you are changed to x, y, spatial domain to u, v. We just give you some quick idea. What does it look like? See? This becomes 2 dimension, right? I have a tofu here, a rectangular post, 2 dimension. Can you imagine the result like this one? Can you? Remember the sinc function, right? So if you look at the x, for example, take a profile here. What does it look like? It should be sinc, right? So take a u, v here. Take a, for example, and this is amplitude. The larger amplitude, whiter. The lower amplitude, darker. So here, if you take a profile, it's just like the same function, right? Major, low, raise up, and then become darker, darker, darker. So it's the same function here. But you have to know, because this rectangle is not square, larger here, lower in width, lower in height, larger in width. So what does this look like? So if you look at the horizontal, a vertical line here becomes thinner. And with domain, it becomes like a profile. It's also thick, but it's a wider thick function, right? So the result will be like this one. So for the Fourier transform, I'm not going to test your mathematical ability, but I want to have a sense. So maybe I will give you some making example. I give result. This one should be the quick one. What's the Fourier transform result? Right? So you have to know the property of the image. You have to know the spatial domain Fourier transform. So this one and this one, maybe your object is different. Maybe your object is become a rectangular is wider height with narrower width. Totally different. Okay, if you compare. Do you catch what I'm talking about? The wider here, thinner here. Why? Because it's thinner here, wider here. Different feature going to represent. So I don't have to know exactly the mathematical formula, but I know which one should be. So that's the way why we have some areas. Because during your temporary process, you cause this some error occur. Some errors in effect. Okay, we'll talk this one next week. And again, next Wednesday we have a small quiz up to chapter 3. Okay, so class dismissed here.可以啊，好，那王小我拿上去就好。对，上次作业这个。哦。